The Juno rocket is Project Jupiter's entry for the Latin America Space Challenge 2022 and represents the final development of the Callisto family of rockets. Juno's design has been in development since 2019, and its design has been constructed as an improvement of the rocket Europa, which was originally intended for SA Cup 2020, winning a total of 5 awards for the team in Latin America Space Challenge 2020 and 21. Juno is a 3.2 meters long rocket with a diameter of 127 millimeters. Its fuselage can be separated into 7 different parts: a carbon fiber nose cone, followed by 3 modules, a solid motor, and fins. Considering the transonic regimen which the rocket will be submitted, the choice of the nose cone prioritized the optimization of the drag force, resulting in the von Karman model, which was manufactured in carbon fiber using resin. Through the lamination process, the tubes for the insertion of the modules were hand-built by the members. Except for the payload, which was manufactured using fiberglass due to radio waves, the rocket's fuselage was made using carbon fiber. In addition, the external region was painted using a polyurethane-based paint, aiming at greater resistance to weathering and increasing hardness and flexibility. The design of the aluminum connections aimed at an easy assembly-disassembling, considering their attachable fittings, without losing quality in the main function of resisting the efforts applied during the flight. Furthermore, the fins remain as carbon fiber with a trapezoidal shape, with the use of an airfoil due to the aerodynamic contribution. Finally, after a study to optimize the shape of the tail, the reached result corresponds to a spherical section made through a mold and manufactured by the members. Juno's recovery is done through means of a single reefed quarter-spherical main parachute, assisted by a ring sail pilot chute. The parachute's ejection system is composed of 2 CO2 cartridges that are fitted to pyrotechnical seal breakers. Inside each of those, there is a puncher and a small charge of black powder. At apogee, the black powder is ignited, launching the punchers to break each of the cartridge's seals. Once the seal is broken, the compressed gas pressurizes the module, resulting in the separation of the nose cone from the rest of the fuselage, ending the ejection of both chutes at once. The pilot chute drags the main's deployment back out of the module, assuring that the main is deployed correctly. At this point, the reefing line is keeping the main chute from fully opening, reducing the parachute's total drag, which results in the rocket's speed decreasing with more stability at high altitudes. As the altitude decreases and the rocket reaches a predetermined level, the disreefing takes place. During this event, another charge of black powder is ignited inside the reefing cutters, splitting the reefing line, which allows the main parachute to achieve its total drag, greatly reducing the vertical speed until ground level. The electronic subsystem is responsible for detecting the correct moment to activate the ejection system and to trigger the disreefing of the parachute. Its structure is divided accordingly into those 2 individual parts. The first part is located below the parachute ejection system and takes care of the initial parachute opening. It contains 2 redundant commercial off-the-shelf RRC freeze altimeters to detect the apogee with high reliability. The second job for the electronic subsystem is to activate the disreefing of the main parachute. The reefing cutter is divided in 2 parts, its activation system and the cutter itself. The first one, which is placed inside the nose cone, uses 2 redundant RRC free for the moment of disreefing. The latter is the cutter itself, and it has 2 redundant combustion chambers through which the reefing line passes that are attached to the mains riser. Below the electronics, there is the payload module, whose structure is easily removable from the rocket. It weighs 4.3 kilograms and carries 3 major parts: the telemetry system, a camera module, and the payload itself. First, we observe the telemetry system, responsible for gathering and transmitting flight data, such as air pressure, acceleration, angular velocity, magnetic field, and GPS location. The system consists of a microcontroller from an STM32 family with an integrated LoRa module and a custom PCB. Besides transmitting data, another functionality is the storage of information by a SD card. There is also a camera in charge of recording the flight. And finally, there is the main experiment, the Earth Horizon System. It was developed regarding the importance of horizon detection for altitude estimation sensors. By this experiment, we intend to test the method's precision and its possible utility as a usual component for further rockets. This module consists mainly of a Raspberry Pi and a fisheye camera. They are used together in order to record the whole flight and process the created algorithms to find the horizon line in each frame and by that estimate the rocket's altitude. To determine the altitude by photos, there are several steps to do with the image. First, we convert the colored image to grayscale. Then, pass it through a Gaussian blur, followed by a candy detector to find all the edges in the picture. With the edges determined, we trace the biggest edge, which will be a curve that represents the horizon. Having this line marked, we find the ellipse that most approximates the curve obtained and project the ellipse into a unitary sphere. Finally, we get the normal vector of the plane that contains the ellipse and use its projection to get the pitch and yaw angles. It is worth mentioning that to determine the accuracy of the developed algorithm, the gathered data will be compared to another altitude determination system embedded in the payload module. Juno has a Class M solid motor that uses a potassium nitrate sorbitol (KNSP) propellant with an addition of iron-free oxide, red iron oxide. The most innovative part of this year's project lies in the propellant configuration, the starport. Looking for a more efficient grain, we found in the star configuration an interesting way to get not only a greater burning surface area at startup, but also slightly increasing our propellant volumetric efficiency. Adding iron-free oxide to the KNSP, we get a considerable increase in the burn rate. The combination of this with the grain's geometry just delivered an almost end motor in our last simulations on GitHub's Open Motor software. Our motor simulations were made in our own softwares, such as RocketPy for the flight regimen and our own in-building software internally known as SolidPy, specifically developed for our solid propellants. The nozzle used in Juno's motor is a curved throat nose. This format provides a certain increase in the efficiency of its operation in comparison to a LASC nozzle designed for the hybrid engine, which had a straight throat. A few months ago, we improved our static fire test to measure not only the thrust curve, but also chamber pressure curve by adding a pressure transducer to our instrumentation system. That additional data in our tests allow us to check and validate our simulations more precisely. The trajectory of the rocket was simulated using RocketPy, an in-house software. Juno has a predicted apogee of 3,663.28 meters, achieving it at 26.292 seconds. So that was a quick overview of Juno, Project Jupiter's next rocket. Thank you for watching.